Hi, my name is Thalita. I am a PhD student at PUC-Rio. My research is about the effect of interfacial rheology on drop coalescence in water and oil emulsions. My advisor is Professor Márcio Carvalho. Our work is motivated by the necessity to understand more about emulsion. Emulsions are a mixture of two immiscible liquids in the presence of an agent emulsifier, commonly known as surfactant. Here, on the left, we have only water and oil, and on the right side, we added one surfactant. If we try to mix only the water and the oil phases, after a moment, they will separate again. But in the presence of surfactant, they can go together for long periods of time. Emulsions are more common than we imagine. Some examples are in our food, cosmetics, pharmaceutical products, in some ink, and even in the oil industry. With several applications, a great number of studies have been carried out to better understand the formation, its properties, and also an important characteristic, its stability. In some applications, they are desired, but in other cases, they can be a problem, as occurs in the oil industry, where the emulsions are formed during all the production process and need to be separated at the end. The separation process is called by coalescence, based on a merge of two pieces of a same phase or miscible phases. When we have the approximation of two drops due to the pressure, the liquid is squeezed out into the bulk, resulting in the convective fluxes of surfactant in the sublayer. Therefore, we can observe that the surfactant concentration is increasing in this direction, creating a weak zone in the middle of these drops. This is a complex problem that involves a multiple flux occurring at the same time. In this video, we can see this process, a lot of small droplets coming together and becoming bigger and bigger until the total separation of the phases. As our objective of this work, we want to understand more about this separation process through the coalescence of two water droplets by the influence of different surfactant concentrations. To perform these experiments, we used amyllic water and an oil phase composed by a mixture of Primol and spand 80 as the surfactant. In this figure, we can highlight the dispositive on the bottom of the cuvette. This is a simple piece in which there are some holes where we can centralize better one of the drops, and that allowed us to run more than one experiment before cleaning all the devices without compromising the results. The interfacial rheological properties were obtained using the pendant drop method, in which we measure the interfacial tension and the elastic and the viscous moduli. Here we have the coalescence experiment set up, composed by a syringe pump used to form the drops, a pressure transducer used to measure with accuracy the time, a high-speed camera, a computer, a light system, a lift, and a cuvette. This is a photograph of our setup. Now, I will present two videos for the process analyzed. In the first one, we have the drops formation. We started with the injection of the first drop volume. Right after the formation, we moved down the cuvette using the lift, and after that, we started the injection of the second drop volume. Observe that because of this device that I talked, the centering of the drop is more precise and we can prevent the lateral sliding of the droplet. We wait to desired aging time. After we moved the drops against each other, as you can see in the second video. When occur the contact, we wait to the drainage of the oil film remain between them. And finally, when the coalescence occurs, we have the drainage time. Here, I will start the presentation of our results. The oscillatory tests were performed with these conditions. We evaluated 4 different surfactant concentrations. The experiment without surfactant showed the interfacial tension value about 14.5 millinewton per meter, but in the presence of surfactant, we observed a considerable reduction of this property, measuring between 1.5 and 2 millinewton per meter. Comparing all the concentrations, there is not a significant difference in the interfacial tension value that should explain the behaviors observed on the coalescence experiments that we are going to see. But the interfacial elastic and viscous moduli could be responsible for these behaviors. So, if we analyze these moduli, in general, the viscous modulus started higher than the elastic modulus, and after some time, they inverted each other. Only for the smallest concentration, we cannot identify better this inversion point, because in the beginning of experiment, the moduli have values very similar. However, as we increased the surfactant concentration, this inversion occurs at different moments and should be related to the adsorption time of the surfactant on the interface. With 1% in weight after the inversion point, the moduli started to rise in opposite directions. For the other 2 highest surfactant concentrations, this point occurred earlier, and after that, the elastic modulus rapidly grew, whereas the viscous modulus steps decrease with time, reaching 0. These results show that we obtained a strongly elastic interface with the surfactant. Here, we evaluated the influence of the aging time before the oscillations on the interfacial rheological properties, only for the highest surfactant concentration. We can see that the properties behavior do not change with the drop aging before the beginning of experiments. If we move the data to begin at the same moment of the experiment without interface aging before the oscillations, the shape of the curves presents similar behavior. Before to present the coalescence results, I need to define the times that are measured at this experiment. We are going to measure the time before the contact of the drops as the first time, called by the aging time, and the time between the contact and the coalescence process as the second time, called by the drainage time. So we are going to have a relationship between them. Here we have this relationship for the surfactant concentrations evaluated. The time referring to the experiment without surfactant is not represented in the graph since the coalescence occurs almost instantly, taking only a few milliseconds, which is much shorter than the others observed. The results are an average of more than 6 experiments with the respective values of standard deviation. When the coalescence occurred, the drainage time showed no dependence with aging time, neither with surfactant concentration. In some cases, the drops did not coalesce. These results are plotted in this graph with time equal 1 hour, only to representation. In this case, we observed a formation of a solid-like interface that can be responsible to prevent this process. With concentration of 1.5%, this phenomenon was evidenced only after 1 hour of drop aging, whereas for concentration of 2%, this behavior began with 10 minutes. In this concentration, the time interval between 10 and 30 minutes was more investigated, showing results with a random pattern. The same aging time presented both coalescence and no coalescence of the drops. As we've seen, there is a formation of a skin that prevents the coalescence process. Despite of the coalescence occurred for a concentration of 1%, we note that for high aging time, the rupture is no longer symmetrical, indicating that there is a higher resistance to coalescence between the drops due to the presence of the skin. But this skin is not strong enough to prevent the event. However, in the second video, we can see that this skin is more structured because even try to deform the drops and after separate them, the drops did not coalesce. Finally, in this third video, when we increase the drop volume, we can see the rupture of this structure. As our final remarks, we evaluated different surfactant concentrations and also the dependence on film drainage time with the interface's aging time for each concentration. When the coalescence occurred, the drainage time did not show dependence with the aging time, neither with the surfactant concentrations. And when the coalescence did not occur, we observed a formation of a solid-like structure on the drop surfaces, representing the strong activity of surfactant migration from the bulk region to the interface, and the formation of an elastic film at the interface. The interfacial tension did not show significant difference between the concentrations studied. On the other hand, the elastic and viscous moduli showed that the surface viscoelasticity plays an important role in the coalescence process. As our future steps, we are going to investigate how to promote the stabilization of these strong interfaces through weakening the interface elastic modulus chemically or mechanically, for example, increase the drop area. I would like to thank to all funding agents and you for your attention.